So this is the lesson on planetary fields, and the reason I'm making this video for you is because when I looked at the PowerPoint, I realized that I specifically designed my new PowerPoints to have less information on the PowerPoints and more about, just images and then me explaining what was going on. So I figured, well, why don't I just explain what's going on? So this is a lesson on planetary fields. I think it's 21.4 in the Kerboodle textbook for this course. And yeah, let's get started. So if we look at my starter question here, where do you think Earth's gravitational field is strongest? And I've given you a little hint here, where gravitational field strength is gm divided by r squared. Okay, so if we look at this, we cannot change g. We cannot change the mass of the Earth, at least not by any significant amount. And so that means that where are we is entirely related to this r squared. Well, because we're dividing by r, a bigger r means a smaller gravitational field strength. That makes sense. Farther away from Earth you are, the less effect its gravity has on you. So we want as small an r as possible. So surely at 0 or very near 0 or the very center, that means that will be the strongest gravitational field possible. Well, let's take a look at why that is or is not right. So this is what we are going to try to learn about over the course of the next 20, 30 minutes or so. And what we got to look at here is you have to remember that technically speaking, this formula is for a point mass. Okay, it is for a point mass. Now, we treat planets as though they are point masses because the distance away that we are when we're doing a lot of these calculations is so big that it's essentially that's true. Okay, that you're being pulled towards the center of mass, it's fine. All the force ends up directing towards the center of mass. Everything is pulling in the same general direction. However, we technically are not a point mass. Okay? So, the thing is, what about when we end up below the surface of a planet? And I have no idea why that 4 is there. I will go back and edit that out later. Okay, so once you get below the surface of a planet, things start to get tricky. So let's take a look at that. So overall, all the force is pulling towards the center of the mass when you are outside or even at the surface of the planet. However, once you're underneath the surface, you are now actually surrounded by mass. And you have to actually realize that this force, F, is actually the sum total of the force from this particle, and this particle, and this particle, and this particle, and this particle, all pulling, all summed together to give you this one force. Okay, so for our purposes, we are going to assume that the planetary body that we're dealing with here has a uniform density as well. It just makes the math sort of easier to understand, but we're close enough that it's fine. So here, you now don't just have force from mass pulling you in a single direction. So you've still got a force pulling you towards the center, and the overall force will end up being there. But you still have, I mean, this bit of mass is pulling you that way. This bit of mass, it's pulling you, that direction, and that direction, and that direction. Now, all of that means you've actually got less mass pulling you towards the center of whatever planetary body. I'm going to actually just start saying Earth because it's easier to think about it like that. So you get less stuff pulling you towards the center of the Earth. And it turns out that the way that it ends up working is that the net force you feel is as if you were on the surface of a planet stupid microphone turning off, as if you had a planet that is the same density as before, but with this new smaller radius, r. Okay, so this new smaller radius. So essentially, all of this mass on the outside, all of the forces cancel out. Okay, now remember that force, the force of gravity is proportional to the radius squared. So like even though there's more mass on this side, it's farther away than the mass on this side. So that ends up balancing out perfectly with our how can I say, with our new formula, our new situation. So the highest gravitational field strength for any planet will be at its surface. Okay. I mean, if you have enough significant figures, I suppose it's right where the atmosphere ends up being thick enough to matter. But there's so little mass compared to the actual mass of the planet that we don't consider that for a solid planet anyway. So you also end up with something interesting where the force of gravity, or the gravitational field strength, ends up varying linearly with radius up until you end up at zero once you're inside of a planet. Now, let's take a look at why that is. So, G is Gm over R. Okay. Or over R squared. Okay. M is rho times the volume, 4/3 pi r cubed. Now, if we combine this, because below the surface of the Earth, mass is not constant, it is a function of the radius. We can combine these so that G is big G times rho 4/3 pi r cubed divided by r squared. Well, that r squared cancels out the r cubed, and we're just left with r. So G, or little g, 4/3 pi big G rho times r. And all of these are constants. It is just a function of r. That's your slope. That's x. That's y. So we've got a straight line that goes through the normal. Now, the reason that we can't use this formula when we are in this region is because the mass is now constant. The mass does not vary with r. Okay, so it's just showing you that why it's a straight line. Okay, so let's take a look at escape velocity. So escape velocity is the speed that an object needs to be going at a point in a gravitational field that it will come to rest at infinity. Okay, so think about it. If you're traveling a certain speed, you are experiencing a varying strength of gravity because you're moving away from the gravitational field. Okay, so the force of gravity is becoming less, your acceleration is becoming less, you are slowing down. And if we look at a velocity versus distance, okay, if you are traveling your escape velocity, you won't reach zero until infinity. And this is terrible. Okay, so you reach exactly zero at infinity. So for this point here, and actually I suppose I should make it velocity versus radius. For this, this is the escape velocity for this point. This is the escape velocity for this point. This will be the escape velocity for this point. So we can see that actually escape velocity also varies with radius. So let's look at how we link escape velocity and all of this stuff. Okay, so we need to look at gravitational potential for this and gravitational potential energy. Okay, so remember that gravitational potential is G m over r. Okay, and therefore work done, or the work that you need to do to take an object from a point to infinity, is G m m over r, or gravitational potential times mass. Okay, so the amount of work that needs to be done is there. Now, an object that's moving has kinetic energy. So if you have exactly enough energy to overcome or to do this work, that would also be your kinetic energy. 1/2 mv squared. So if I do a little bit of rearranging, you know what, I'm going to rewrite it all. 1/2 mv squared is equal to, that's a little v, is equal to big G, big M, little m over r. Well, this little m and this little m will cancel out, so that actually means that the mass of whatever object you're trying to have escape the gravitational field is irrelevant. As long as it's moving at this speed, it will be able to escape the gravitational field. rearranging again, V ends up being equal to the square root of 2gm over r. Okay, so that's your escape velocity formula. You need to know how to derive it because you are not given it on a formula sheet. So you do need to know how you are going to apply that. Now, calculate the velocity needed to escape the solar system for an object in Earth's solar orbit. So the question that I'm trying to ask there is basically, how fast did we have to make Voyager go if we wanted to escape the solar system? So I'm not trying to escape Earth. We're trying to escape the sun. So we have to use the sun's mass from our formula sheet. Sorry, I'm just going to call up my formula sheet. Okay, but either way, I'm going to start putting in my formula. So V equals square root of 2 big G, big M, and in this case, it's the mass of the sun divided by the radius. We're given the radius. So square root of 2 times 6.67 times 10 to the negative 11 times, so we need solar mass, which on my formula sheet is 1.99 times 10 to the 30. And we are looking at 149.6 gigameters. So if we then math this out, okay. What did I say? 1.99. Okay, and my radius was 149.6. So we are looking at 42,124 meters per second, or approximately 42 kilometers per second. That's a big rocket. To give you an idea, to escape Earth's gravity, we're looking at around 11 kilometers per second. So that's 4 times much to get away from the sun, and we're so far away from the sun. So there is a reason that actually we did something called gravity assists. So we used the momentum and the gravity of planets like Saturn and Jupiter to actually accelerate our probes out of the solar system. But yeah, it's fast. You have to be moving very, 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 very fast. So here, this is the gravitational potential of a planet as how it varies with distance. Remember that gravitational potential is negative because it means that um, in order to get to infinity, we must do work on the field, whereas an object in the field will have work done on it naturally. In other words, the gravitational potential will automatically turn into kinetic energy and it will move towards the object. In other words, if I've got an object here, it will fall into my potential well. Okay, it will move towards the surface of the Earth naturally. Now, if I'm going to relate this graph to my potential gradient, in other words, the rate of change of potential as it varies with distance, well, very easy. Your potential gradient is the gradient of this graph. In other words, if I'm really close to the planet, it's a big potential gradient, meaning that the gravitational potential changes very quickly with respect to r. However, the farther away we get, the flatter that line becomes. So the farther away you are, in order to have a more noticeable change in your gravitational potential, you have to move a greater r. So that's how gravitational potential and gravitational potential gradients are linked. Okay, so hopefully that will help you out. Yeah. Good luck with the exam questions and whatnot.